I have a sample tree up here that we're going to use to look at this definition. So this is the definition for a rooted tree. And this tells us that a rooted tree is a digraph formed from a tree by designating a vertex as a root and directing each edge away from the root. So in a textbook example, you probably see they choose something like this vertex or this vertex as the root. I want to explore this from a little bit different perspective. I'm going to choose something like this vertex here as our root and explore what happens when we apply this definition to this graph. This graph is a tree. You see there's no cycles. Everything's connected. So it meets the definition for tree. So now we're going to designate this vertex R. This is going to be the root. And so now to create the digraph, which is a directed graph, we have to add directions to each of our edges. And according to the definition, the digraph is formed by designating the vertex, which we've done, and then directing each edge away from this root, this vertex. So if this is my vertex, then I want the direction arrows to go away from that on each edge. And then I'm going to continue this so that as we create this path continues in the same direction and we have a progression away from the root. Down here we kind of turn the corner and I'm going to fill those in, and so we have this down here. What happens up here? If I put an arrow going this direction, am I going back towards the root? Because it appears that I'm physically moving towards the root. Is that the case? And does that violate the definition? Think about that. All right, to help us answer the question that I posed here, we're going to look at this. I've designated this as graph U. This graph is isomorphic to the original graph that we have, which means that it has the same types of property and structure as this graph, only it looks slightly different. Namely, this upper piece here has kind of been folded out using this vertex as a hinge. And so we see that if we do in fact add this direction to this edge, that's adding this arrow in this direction, which is going away from the vertex that we've designated as the root. And so we continue the directions out this way. Our directions continue out this way. And so we have, by definition, created this rooted tree, which is a digraph. It's a directed graph, but it's specifically a tree graph because it fits the definition of tree. And so this is a way to help us explore if we really understand and can use the definition. If we choose something that doesn't quite look like a textbook example, by choosing a vertex in the middle rather than at some physical end of the diagram that we're given, that helps us apply this definition and analyze what's really going on. Let's take a few minutes to review. Can we identify which graphs are trees? So I want to go through and look at these 4 examples and see if we can determine the types of graph that we have. So in example A, do we have a tree? So we're looking for a couple of things. 1, we're looking for something that doesn't have a circuit. And 2, we're looking to see if everything is connected. So do we have any place where we can start at a vertex and go around and return to that vertex? As review, I have the definition of circuit here, so it's a path that begins and ends at the same vertex. We don't have that here, and so this is a tree. So let's look at part B here. B shows all my vertices are connected to each other, except for there's a gap here that doesn't connect this part to this part. Looking at just the left-hand side, we see this is a tree, everything's connected, and there's no circuit. Looking at the right-hand side, everything is connected, there's no circuit. So we have two trees that create the graph in B, and so this is not a tree but a forest, since there are two trees here. All right, and so the next one we have going from left to right, all the vertices that you see are connected to another vertice. There's no gaps in this graph. And so we have this very tree-like structure until we get to here. And we have this triangular form right here, which is a circuit. If we start at this vertex, we can go to this vertex, and we end up back at this vertex. And that is a path that begins and ends at the same vertice. And so this fails to be a tree, and it also can't qualify as a forest. All right, and then D is one vertice. And D is one vertex. So is this a tree? All the vertices in the graph are connected because there's only one, so it's kind of by default. And so there's no other pieces to this, so it meets the definition of a tree, and this is what we call the trivial tree. So if we were looking for which of the graphs that we had to choose from were actually trees, the answer is A and D. All right, the next definition we're going to look at is spanning tree. A spanning tree is a subgraph of another graph, and it's going to include all the vertices of the original graph, but also be a tree itself. So, for example, we're going to look at this graph G, and we're going to find the spanning tree contained in G. So we're basically creating a graph out of an existing graph, but we want it to specifically be a tree and contain all of the vertices in here. So you need to find a place to start and then move from there. I'm going to start on the right-hand side of this graph, and I want to keep this vertex, and I'm going to move this direction and keep this edge and this vertex. Now, I need to find a way to start to gather up these vertices without creating a circuit, and everything has to be connected. So I'm going to need to come back here to grab this vertex. I'm going to need to move forward to grab this vertex, and I'm going to need to move forward to grab this vertex. Now, I missed this vertex. I haven't gotten this one or this one yet. So where can we go with this? So one thing that I could do is I could move backwards here and grab this one. Now you might think I've completed a circuit at this point, but I haven't, because I haven't included this edge. I haven't highlighted that edge yet because I don't really want that edge, and I don't need that edge because I've gotten this vertex, I've gotten this vertex. I don't need that edge to create my spanning tree. Remember, our goal is to take the existing graph and create a tree out of it. So I'm also going to move forward from here, and I'm going to grab this vertex, and I'm going to move forward from here and grab this vertex. So let me redraw what I've created down below here. So I'm going to just copy my vertices. So there's my vertices. And I came forward and I connected this I came backwards and I connected this. I came forward and connected this. I came forward and connected this. Then I went backwards and connected to here. I went forward and connected to here, and then I went forward again and connected to here. So did I in fact meet my goals? Well, I definitely included all of the vertices, so I met that goal. Did I create a tree? Everything's connected, so that's part of the definition for tree. Is there a circuit? If you start at any place, can you return to that vertex? I don't have a circuit, so I have created a spanning tree. You may have looked at this graph and found another way to create a spanning tree in here, and that's fine. They don't have to look the same to have met the goals of the definition. So this is our spanning tree that I found. Perhaps you have another. Cheerful calculations.